All right, and welcome back. So in this video, we're going to be comparing linear, quadratic, and exponential models, and we're mainly going to be seeing them within tables and within graphs and graphs of their respective tables. So without further ado, let's begin. So the question proposes which represents a linear, quadratic, and an exponential function. We have three different tables here. One of them is going to be representing a linear function, one will be representing a quadratic function, and one will be representing an exponential function. And it's our job to establish which one is going to be. So let's just look at the first example, the training heart rate. So what we always want to look for is, can we see a pattern, right? We've discussed linear patterns before, where if we can calculate a slope, a constant increase or decrease in our y's, over the same increase or decrease within our x's, right? That's how we determine our slope. For a exponential, we try to talk about, can we establish a common ratio, right? Are we multiplying by 2 every single time? Are we multiplying by 1/4 every single time? And a quadratic we haven't really talked about, and we're going to be doing that today. But let's proceed with the question and see if we can use that development of patterns to help us out. So within the first chart, the training heart rate, I see that I have an increase of 10 in my age every single time. So I'm just going to write that one, plus 10. And let's see, can I establish some kind of pattern within my y's, or the beats per minute? Well, it looks like I'm going down 8.5, then I'm going down another 8.5, and again I'm going down an 8.5. So this is going to be a linear function. All right, what about within the middle? So I have a time of 0.4, 0.81, and 1.2. I don't really have a consistent change there at all. So we can potentially rule out linear. Just because there is not a consistent change, we can look at the differences between them to see if those are consistent. But what I like to look for is my y values right here. I have 10.44, 12.76, then 12, and then 9.96. We can see that it's kind of going up and then down. We're starting at 10.44, and then we're increasing to 12.76, then we're decreasing to 12 and decreasing to 9.96. So this is going to help me determine that this is going to be quadratic. It has that up and down shape, right? Or, well, I should really do it this way. It has the up and down shape like that. So we can establish that this is going to be quadratic. Okay, and now let's look at the volleyball tournament. Well, I have a increase in my x's of 1, which is promising. But if I look, I have 16, 8, 4, and 2. Well, I'm getting reduced by half every single time. So since I'm going down by 1/2, then 1/2, and 1/2, then I can establish this is going to be an exponential. It's easier for us to determine this if we look at their respective graphs. As you can tell, within the linear model, well, I have what appears to be a straight line. For the quadratic model, again, as we noted in our pattern or our observation, we have that up and down, that parabola look. And if we look in the volleyball tournament, we seem to have an exponential decay curve. So it's easier for us to look at a graph, but today we're going to be going through and how to look at a table to help us establish what's linear, quadratic, and exponential. Great job so far, folks. So this example says graphing data to choose a model. It says graph each data set. Which kind of model best describes the data? So plot the data points and connect them. Well, I kind of already gave it away. It says the data appears to be exponential. And if we look at the graph, we can see that it tends to go in an exponential rate. But to back it up, we always want to look for patterns. Patterns is the key idea here. Can we establish any patterns? Well, if I look at my time, or my x's, I'm going up by 1, which is great. So I'm going to put plus 1. But if I look at my y's, I'm going from 10 to 20, 20 to 40, and 40 to 80. Can I establish a pattern there? Yeah. I'm doubling it. I'm multiplying it by 2. So since I have a common ratio, that's why I can establish that this is going to be exponential. Now, if we want to write a function for this, we totally can. The way that we do it, again, it's always y is equal to ab to the x, where a is your initial value and b is your common ratio. Well, you want to look for your common ratio. Well, did we establish our common ratio? Yeah, we did. It's 2. And I had that in green, so I'm going to go back and I'm going to change this a little bit. So our common ratio was 2. So now we have y is equal to a times 2 to the x. Now we need to establish, okay, what's that initial value? Well, we can do that in a chart. If we're given the table, look, we have when x is 0 or y is 10. Well, so when our x is 0, y is going to be 10. So we can fill in that information. When x is 0, y is 10. We know that, I should put that in blue. Whoops, all over the place today. Come on, eraser, there we go. You know that anything raised to the 0th power is 1. So we get that 10 is equal to a times 1. I mean, yeah. So then we know that our a value is going to be 10. So our starting value is going to be 10. So all together, we get y is equal to 10 times 2 to the x. And that's how we can create a function of our exponential model. Nice job, folks. Let's keep it going. Graph each data set. Which kind of model best describes the data? So let's see if we can establish anything first before we graph it. That way we can go through the tougher part in the beginning and then verify it with the easier visual model. So we always want to look in our x's. Do we have an increase in our x's? That's a constant rate. Yeah, it's great. We're adding 5 every single time. Perfect. Okay. Do we have a constant change in our y's? We go 32 to 41. Well, I added 9. 41 to 50, I'm adding 9. 50 to 59, I'm adding 9. Look at that. We're finding that we're going to be having a linear model here because we have a constant slope. Well, let's verify it. Look at that. Okay, we can now verify it with the graph. Now, if you weren't given the graph and you were to graph it first, that's totally okay. That's totally fine to graph it first and then try and establish a pattern to verify it. That's totally fine. But I just want to go through how to do it on a table and then verify with the graph, because doing it on a table is a little bit different and it's a little bit more challenging when given a set of points or a table set and then compare it to a graph. So I want to go in that method. And that's the reason behind it. Look for a pattern in each data set to determine which kind of model best describes the data. Again, we're looking for linear, quadratic, or exponential. Well, let's see. Do we have any change in our x's or in the cable distance from tower? Going from 0 to 100 real quick. 100 to 200, 200 to 300. Yeah. So I have a change in 100, which is great. Do I have any changes in my y? Going from 400 to 256, 256 to 144, 144 to 64. Let's think about that one. Well, I'm subtracting a lot and I don't have a constant ratio that I'm decreasing by here. So what now? Well, here's what happens. If we don't have a constant ratio, we can eliminate the exponential model. We don't have a common difference or a common slope between it, so we can eliminate the linear model. So now we're left with either a quadratic function or just a random scatter plot. right? Because that's totally possible to have just random points on a scatter plot without it being a consistent function. But here's something that's really cool with the quadratic method. Let's look at the difference between those differences. So notice in that second difference, we have adding 32. That's what's going to establish us to be a quadratic expression. So since we have a constant change of the distance, there's a constant second difference now of adding 32. So the data is going to be quadratic. And that happens all the time. With a quadratic function, if you have a non-constant change in your y, but you have a constant second change in your y, that's going to lead you to a quadratic model. It's cool, right? It's awesome. Math. No! Gotta love it. Gotta love it. All right, and let's see if we can establish anything here. So we're given the value of a car, and we want to determine what kind of method or what kind of function would this appear to be? Is it going to appear to be linear, appear to be quadratic, or is it going to appear to be exponential? So again, we always want to look for patterns. Do I have a pattern in my y's? Yeah, or my x's, I should say. Yeah, we are consistently adding 1. That's great. Do we have a pattern within our y's, though? Well, I'm decreasing by 0.85. Okay, I'm losing 15% each time. So since we have a constant since we have a constant ratio of decrease or increase, but in this specific example it's decrease, then we're going to have a exponential graph, or an exponential model, I should say. Cool, awesome. All right, and one more to go through. So this is going to be a multi-step problem where it wants you to describe the situation in words. So in order for us to do that, we have to look at the table and say, what is it telling us? Well, we're talking about ladybug population. And my x's is the time in months, and on the y's is the ladybugs, right? So we need to think about, okay, what is it really trying to tell us here? Well, it's trying to tell us about the population of ladybugs. And each month, the ladybug population is multiplied by 3. In other words, the population triples each month. And we can look at that to see, oh, well, yeah, it's true. For every 1 month that passes, it triples, right? And now we want to write the function. So in order to do that, we establish it's going to be exponential because our common ratio is going to be 3. So we want to start out by writing our general form, y is equal to ab to the x. Remember, the x is only raised in the power of b. Want to substitute for the common ratio. So our common ratio is 3. We're going to plug that in for b. So now we have y is equal to a times 3 to the x. We want to choose an ordered pair from the table such as 0, 10. If you are ever given your x value being 0 and a respected y value, use that. It's going to be the easiest one for us to use. And then we want to simplify 3 to the 0th being 1. Then we find that the value of a is 10. So that means that our starting population is going to be 10. And then we can substitute it back in. Then we have y is equal to 10 times 3 to the x. And that is how we describe an exponential function, and then how we can go about figuring out the function of the exponential given a table. Great job, folks. Today is a little bit lighter. It's a lot of review, and I get that. So thank you for sticking through with it. You have been great. If you have any questions, please feel free to reach out, and have a great day.